Good morning. I'm Jane Platt with the Media Relations Office at NASA's Jet Propulsion Laboratory in Pasadena, California. We are now just 3 days away from a very big day on Mars. This Sunday, August 5th Pacific time, late in the evening, which is early morning, August 6th on the East Coast, the Mars Science Laboratory and its Curiosity rover will touch down on the red planet. The rover will investigate the landing area, the site around it, to see if it has ever provided any environment favorable for life. Today we're going to find out more about the science of the mission, and I'd like to start out by introducing our panelists. We're going to hear from Michael Meyer, the lead scientist for the Mars Exploration Program from NASA headquarters, Washington. John Grotzinger is the Mars Science Laboratory project scientist with the California Institute of Technology in Pasadena. Don Hassler is the principal investigator for the Radiation Assessment Detector on Mars Science Lab. He's with the Southwest Research Institute in Boulder, Colorado. And Michael Malin, the principal investigator for the Mars Descent Imager on Mars Science Lab, and he's with Malin Space Science Systems in San Diego. We're going to start things off this morning with Michael Meyer.
Well, thank you. I can't wait. You know, August 5th, 10:31 p.m. Pacific time, Curiosity lands. It's then when it begins its trek up Mount Sharp to unveil the present and past environments of Mars. I just can't wait. So Curiosity has the goal of understanding and determining the habitability of Mars. And what do we mean by habitability? Well, you need three things, we think, for life. One is a solvent, in this case water. One is you need something for structure, so we need carbon compounds, and you need energy. Those three things, we believe, are the necessary ingredients for life. Interestingly enough, over the last 15 years, we've been able to explore Mars extensively from orbit and some on the surface. And what this has shown, at least in the past, Mars looks like it has been habitable. It could have supported microbial life. But this is from orbit and some roving on the surface, and it makes us believe that we're going in the right direction. But you know, you need to go and look and you need to ask the right questions. And Curiosity is a rover that's able to do that. How do we narrow this down from looking at Mars on a global scale of a potentially habitable planet to going to a specific place where we can test this hypothesis? Well, over 4 years, we've had a science community looking at different landing sites on Mars that have provided a wealth of information from our orbiters Odyssey, Mars Reconnaissance Orbiter, from past missions like Mars Global Surveyor, and also information from our landers of Spirit and Opportunity have really helped us figure out what Mars looks like and what it looks like in specific places. So what the science community has done is looked at all the potential landing sites, narrowed it down to 4 prime sites, all of which demonstrate evidence of water geomorphologically, so it looks like there was a lake, there looks like there was a river, and also mineralogically. So the minerals that we see are indicative of having interacted with water, and minerals such as clays and sulfates. So with that, the 4 prime sites, all of them suggest habitability in the past, and then it was narrowing it down to 1 landing site. And with that, we ended up picking Gale Crater because in the middle, there's Mount Sharp, a huge mound of sedimentary layers that provide us the opportunity to start in the past of Gale Crater and rove up the surface of Mount Sharp and come through time to see how the environments have changed on Mars. And to give us more specifics about the landing site and how Curiosity will investigate it, I turn it over to John.
Thanks very much, Michael. I am absolutely thrilled to have the chance to land the spacecraft on the surface of Mars. And when we do, we will have started the era of a whole new dimension of space exploration and on the surface of another planet. And this is the dimension of deep time. Time measured not in hours, days, years, events that happen today or tomorrow, but hundreds of millions to even billions of years of history recorded in the evolution of a planet that's kind of like our cousin. And at the time that we will explore, billions of years ago on the surface of Mars, we hope to investigate these possible habitable environments. And we have chosen the most spectacular field site. It just continues to give. And what I want to do is finish today by showing you what the science team is doing this very moment as you all sit here. They are working away at mapping some of the details that we'll have a chance to explore. So let's go to the first graphic. And this is something that you will have seen before. It's a MOLA topography map of the surface of Mars. And what we see when it eventually comes up, there we go, is the dichotomy boundary, which is the geomorphic feature that separates the flat northern plains of Mars, which are geologically younger, from the southern highlands, which have lots of big ancient impact craters. And you can see on that topographic image even the topography of ancient rivers that flowed across the surface there. So point number one is that without getting too clever, the most basic observation you can make is that water flows downhill, and we have chosen one of the lowest spots on Mars that looks geologically fascinating to go to. It's even lower in elevation than the floor of Valles Marineris, which has often been viewed to be a great destination. And so there, in that sort of pink and white patch of topography, that's where we're going to land, right up there where the arrow points to. Now, if we go ahead to the next graphic and zoom in, here we are now at the landing ellipse, and there's Mount Sharp, the very peak of which, if you go from the landing ellipse up to the top of Mount Sharp, that has more elevation than Mount Whitney does, which is the highest mountain in the lower 48 states here. And so it's about 5 kilometers high. And the most extraordinary thing about Mount Sharp is that it's layered. The entire succession is layered, giving us a recorded history of probably what represent hundreds of millions of years of time, maybe even 1 billion years of time, 3 to 4 billion years ago, when the planet may have been more like Earth had been. Okay, so we're going to land in that ellipse, and now what I want to do is turn your attention to the ellipse, because we've said a lot about Mount Sharp in previous meetings together, and I want to tell you more about what's going to happen in the ellipse now. Okay, next one, please. What we have realized as a geological community, and this led to the selection of Gale as a landing site, because Gale is what we call a go-to. You land in a flat place, you drive somewhere else, and really what you expect is that all the excitement will be somewhere else. But it turned out that, we were concerned that if there was an anomaly with the spacecraft and we had to spend a big chunk of the mission in the landing ellipse, we better have something good there. So we always knew this Alluvial Fan was there. But what happened was, about a month ago, it became clear that we needed to do more work to tear into the details, because where the landing ellipse is right out in front of that Alluvial Fan, and there, I think, presents an extraordinary opportunity for what might be a really great science discovery early on. This has lots of potential, because an alluvial fan is a feature where water flows downhill. And so when we look at that fan shape, we descend in topography about 150 meters from the top of the fan in the upper left of the screen. And as we go down to the bottom, we go downhill and downhill. And this feature looks just like the kinds of things that are formed by water on Earth. And we've always wanted to land on something on Mars where we looked like water was flowing in advance. Well, here it is. So there is some chance we could actually land right on this feature, or land right out in front of it, where you always wonder, where does that water go if it goes down the alluvial fan? Maybe it goes right into where our landing ellipse was. Okay, so that's a topographic map that shows you that we go downhill from the alluvial fan into the landing ellipse. Now the next image, please, superimposes on top of that topography a property that has been mapped on previous Mars missions called thermal inertia. And what this really means is it's the property of a rock to basically retain heat relative to surrounding areas. So with the Themis instrument, for example, we can take images during the day, we can take images during the night, and what we see is that anything that's colored in red there tends to stay hotter longer as we go into the evening. It keeps its heat. Now, what kind of material could do that? Lots of non-uniqueness here. There could be lots of things that could do that, but one of the things that we're attracted to as a science hypothesis that we would like to test is the possibility that there were loose surficial materials once transported by water that then became cemented in the presence of water. And so right away we can start to look for minerals that bound the particles together that tell us about the previous history of water there. And that's an exciting possibility because that already begins to sort of sniff a little bit like a potentially habitable environment that was very old. Okay, now if you just go back and forth here a little bit, what we can see is there's the topography. Here comes the thermal inertia. Notice that that red is at the very end of the alluvial fan and out in front of the alluvial fan. So there's a boundary where the morphology evidence ends and where the physical properties evidence sort of steps across the alluvial fan there. We're really excited about this, and it suggests to us right away that we've got some cool geology to do ahead of us. Okay, now in the next one, so here's what we did. We divided the area up, and we started a sort of a crowdsourcing effort. This is a science team of over 400 people. Some of them were really looking for something to do. So we divided these quads up, and basically what you see here are 0.025 degrees of latitude and longitude, dividing it all up, and then basically I sent an email to the team and I said, anybody that wants to take a swipe at this is welcome to jump in, roll up their sleeves, and start doing some mapping. So they did that, and I'm not going to show you today with the progress of the mapping that we're doing, but I'm going to show you why we're doing it. And we're going to pick a quad that's right in the center there, number 50. Very close. We could actually land on that one. So here we go. And what you've got here is really kind of a geologist's paradise. This is in the middle of the landing ellipse. You've got a crater there, which is 250 meters diameter, which is about halfway in size between Endurance Crater and Victoria Crater. Remember, those are what we explored with Opportunity about 7 or 8 years ago. And in there, in the crater, you see the layering. So right away, we know we've got something good to look for there. But wait, because there's a scarp that runs along through the image as well, and that's the kind of terrain that Spirit explored. So when we went to a place called Home Plate, the home plate was sort of a circular outcrop, kind of looked like a home plate, but it had a scarp about 1 meter or 2 in elevation. And this is probably a little bit less than 1 meter or 2. It could be 0.5 meter to 1 meter in elevation. And basically, we get the best of both rovers from MER. We get craters that have punched into the bedrock, and we also have probably wind-driven abrasion of the bedrock to expose these layers. No matter where we land, what we now know from studying the details of these quads is that we're going to have something exciting to do. So that's it, and I'm going to turn it over to Don to talk about the science we've been doing in cruise.
Thank you, John. So one of the unique things about MSL is that we've actually been doing science during cruise since about 10 days after launch. The Radiation Assessment Detector, or RAD, was turned on December 6th, and we've collected a little over 7 months of data before we were turned off in preparation for landing. And so the primary objective of the radiation assessment detector is to characterize the radiation environment on the surface of Mars. And that's essential to understanding habitability because it's a life-limiting factor to habitability. But we also realized that we had this opportunity to collect data and take observations during the cruise phase. And that's essential also because as in planning for future human exploration of Mars, we need to understand what the radiation environment that future astronauts will experience both during cruise but also during the surface. So if you have the first slide, please. Basically, all the planets, Earth, Mars, are bathed in 2 types of radiation. Galactic cosmic rays, which come from supernova remnants deep in the galaxy, and they vary on long time scales. We're also bathed in solar energetic particles, which come from the sun, or flares or explosions on the sun, which happen episodically with the solar cycle, and they can be very short but also very intense. And so characterizing this radiation environment on the surface of Mars and in space during cruise is the primary objective of RAD. So if we have the next graphic. The real question is, so why do we need to measure this on the surface of Mars? Well, the radiation environment on Mars is fundamentally different for two reasons. One is Mars doesn't have a global magnetic field protecting it from the charged particle radiation in space like the Earth does. Mars lost its magnetic field several billion years ago, and so it's pretty much bare and vulnerable to the deep space radiation which is present. Also, Mars doesn't have well, it has a much thinner atmosphere than Earth. It's about 1% the thickness of the Earth's atmosphere. So there isn't as much effective shielding or mass to absorb the particle radiation coming to it. So characterizing the radiation environment, measuring the radiation environment on the surface of Mars is essential for understanding the questions of habitability in terms of life-limiting elements of habitability, but also in planning for future human exploration. So if we could have the next slide. So this graphic shows two spacecraft. One on the left is the Mars Science Laboratory during cruise. It has the descent stage, the heat shield, the back shell, but it also looks curiously similar to the Orion spacecraft, which future astronauts will use to journey out off into deep space to the asteroids and potentially Mars down the road. 20, 30 years. So measuring the radiation environment inside the spacecraft was something that we actually realized about a year ago. We weren't originally planning to take observations during cruise, and about a year ago we realized that this was a great opportunity because most of the time when you want to measure the radiation environment or the energetic particle environment, you put your detectors on the outside of the spacecraft to measure the pure interplanetary environment. But RAD is deep inside the spacecraft, in the belly of the spacecraft, basically as a future astronaut would be tucked in the belly of their spacecraft on a future mission to Mars. So we took these 7 months of data, and if you show the next graphic, this shows sort of a summary result of the particle flux that we observed during cruise phase. So it started on December 6th, 10 days after launch, and it went about 7 months and a week till July 13th when we finally turned off. And you can see two things in this plot. You can see this is a particle flux versus time, and you can see the galactic cosmic ray background, which varies slowly over an 11-year solar cycle. And then you can see these spikes. There's about 5 spikes on the graph, which show the results of solar energetic particle events as the result of solar flares or explosions on the sun, giant storms on the sun. And these came without a moment's notice. They happened very quickly. They lasted a few days, and then they were gone. But you can see that the particle flux that RAD observed, even deep inside the spacecraft, went up over an order of magnitude. So let's focus on one of the large events in March, if you show on the next slide. Just centering in on this region here in March. There were 2 storms, 2 events back to back. And if we have the next graphic, this shows a blow-up of this region. So the white data is the RAD observations, which, as I mentioned, they increased by about an order of magnitude in terms of the particle flux density. But the red is the pure deep space environment measured from the SIS instrument on the ACE satellite, which is pretty much along the line that the storm came from the sun. So the measurements that we see in red would be what RAD would experience or what an astronaut would experience if they were on a spacewalk in deep space. And so the shielding or the protection from the spacecraft reduced the radiation environment by about 2 orders of magnitude. And that's essentially what we're going to learn from these cruise observations, in addition to comparing it with these other events that are observed from other spacecraft. But the lesson here is that these events happen very quickly, and they can be very intense, but with the proper shielding, we can help plan for and prepare for future missions to Mars. So I'll pass it on to Michael to talk about the cameras, which we'll be observing as we come through the atmosphere.
Thank you, Don. I'm here actually representing about 3 or 4 different teams. I'm the principal investigator of the mast cam, which are the science color cameras on the mast of the rover. I'm also here as the principal investigator of the descent imaging system, which will take pictures during the descent. Ken Edgett is the principal investigator of the Mars hand lens camera, which is MOLLE, it's called. Roger Weens is the PI of ChemCam, which is the laser that measures composition, but it also has a camera called the remote microscopic imager, which will observe the actual location where the laser blasts. And finally, Justin Mackey, who is the lead for the engineering cameras, which are really the workhorse cameras on the spacecraft. There are 17 cameras on the spacecraft, and you might ask, why are there 17? The first graphic shows me 39 years ago, walking across a stream in Alaska, and it looks like I'm carrying someone. I'm actually, because my boots are around my neck, but the thing on my back is my 80-pound pack, and at the very top of that is a bag with 4 cameras. Geologists go in the field these days with lots of cameras, and the next graphic shows the rover, and it has lots of cameras that can be grouped into 3 different groups of cameras. On the mast, which you see at the upper left of the graphic there, are 7 cameras on the mast. Those are two pairs of navigation. Pairs because there are 2 sides of the rover computer, so each side can control one set of lenses, one set of cameras, and there are pairs of them because they're taking stereo data. So there are 2 pairs of navigation cameras. There's a single pair of mast cameras, but in fact, they're really 2 different cameras. One is a sort of a 34 millimeter camera, which is very much like a 35 millimeter camera that you would normally have on your digital camera. The other is a 100 millimeter telephoto lens. And then the RMI is inside the ChemCam at the very top there. There is 1 camera on the turret, that's the Molly. That camera can get very, very close to the surface. It can resolve things when it's at its closest that are only a few tens of microns across. And then fixed to the body of the rover, and they can't move other than with the rover as it moves around, are the HazCams, the hazard cameras, which are used to look for where to put the robotic arm and also to look for hazards as the vehicle is driving. There are 2 pairs on the front and 2 pairs on the back. And finally, there's the descent camera, the MARTI, which is off on the side there. And one of the wheels will actually show up in the MARTI data. The next graphic shows, I think, is a video which we made of during a test where we show why we have so many different cameras. It's going to be a zooming in. This is a navigation camera, and it shows you sort of what we get with it. This is the 34 millimeter mast cam. This is now this is going to transition to the 100 millimeter mast cam, and finally with the view that Molly can get, and we'll zoom in on that as well. So the idea is that we can cover a range of resolutions from a few millimeters down to microns in scale, and the 100 millimeter mast cam at 1,000 meters distance has a 7.5 centimeter pixel, which means something about this big could be easily resolved about 0.6 of a mile away. The next graphic, now I'm going to switch gears and start talking about my baby, is the MARTI, the Mars Descent Imager. Give you an idea of the size. This is the same knife as you see in the picture. Geologists almost always use their pocket knife as a scale for small things. Normally, they also use rock hammers, but I didn't bring that with me. The MARTI is a fixed camera, fixed focal length, fixed aperture. It takes images at about 4 frames per second. And they're color. They take color the same way your consumer camera takes color. It has a color filter on top of the detector, and that color filter is then used. We interpolate between the color filters to make a full 3D, full color image. As MARTI moves across the surface during the descent, it will in fact take stereo images, mostly because the descent system is moving. The next slide shows how we're going to get the data back, or what's the pattern of it. You'll be hearing later today, I think, about the descent by the EDL itself. I had to learn a lot about EDL in order to be able to figure out how to get the images back. Because once we've taken them, they're stored, then we have to figure out what sequence to bring them back in. This graphic shows the basic phases of the descent and my attempt to bracket all the possible descents. The issue is really that the parachute descent takes longer than everything else, and it also can vary by a large amount. So the sky crane, which you'll hear a little bit more this morning, takes about 15 plus or minus 3 seconds. It's a very, very well-prescribed set of things that happens, and it's a very short interval. The power descent takes about 53 seconds plus or minus 3 seconds. So there's a very, very well-defined period of time when we know the vehicle is under power and when I could know which images would be coming back. However, the parachute descent could take anything from 45 seconds if the vehicle comes in low to 200, 215 seconds if the vehicle comes in high. That is a huge uncertainty for me to know which pictures will have the most important information. So what I did is I took the absolute longest and absolute shortest time that was ever simulated by the EDL team, and those bracket the 1% probability at either end and also the middle. So these 5 bars here are those 5 cases of the 1% long or short and the 50% time and then the maximum minimum. And I said, okay, project, how many pictures can I get back? And we agreed that I'd get 18. So those white lines that you see there numbered 1 through 18 are my attempt to divvy up all the pictures that I can bring back in the earliest phase of the mission. Those are images that will get something no matter what we land, so or how long it takes to land. So you can see that in the short duration, landing 109 seconds, only images through 7 are actually taken while the vehicle is above the ground, and everything from 7 to 18 are taken after the vehicle has landed. But then as you move out to the longer ones, you can see more images come back. And I spaced these so that I would ensure that we would get at the very least 3 images during parachute, 3 images during power descent, 1 image during sky crane, and potentially 1 image of the dust being raised as during the flyaway phase. And that's sort of why those are variously spaced and not equally spaced along the line. So the hope is that by pulling these back out of this long sequence, the sequence is 1,504 images in length, which is like 6 minutes and 25 seconds or more. That's how long we'll be taking the video during the descent, but most of that's going to be on the ground, and we'll be watching dust and other things in the sky. I think I have one last graphic. Yes, so in an attempt to lower your expectations, these are all going to be thumbnail. The thumbnails for the science cameras are bigger than they are for the engineering cameras. They're 192 by 144 pixels. So they're sort of YouTube sort of resolution, the poorer YouTube. And they're going to be in color. They are JPEG compressed for those of you who are knowledgeable about what your cameras do. Our cameras have a RAW form and a JPEG form, and the JPEG can be a different quality, just like you can set your consumer camera to a different quality. These will be coming back at quality very good, but not excellent. And so they're a little bit smaller, and small is good in terms of downlink. So they'll have artifacts, they'll be small, but we hope that we'll be able to actually tell where we land within the first few minutes of having them back on the ground. And with that, I'll turn it back to you.
All right, thank you, and thanks to all our panelists this morning. We're going to start the reporter Q&A session now, and we do have some reporters who are listening and watching from other locations, but we're going to start right here at JPL. If you do have a question, please raise your hand and wait for the mic to come to you. And when you do get the mic, please state your name and your affiliation. Okay, let's get a mic over here to row 3. Okay, we're just.
Hi, Eric Ham with Nature. My question's for John. Talking about the Alluvial Fan, this is entirely different from now. This is a very recent phenomenon from the recent past. Can you describe when you think in Mars history the Alluvial Fan was made? And, presumably this is a drier time in Mars history, so how could there have even been significant water to take these sediments down the crater wall.
Eric, we only heard the last part of that question. Could you just repeat the very first part?
Describe the timing and environment of this alluvial fan and when it occurred.
Well, as you might guess, Eric, we don't have an easy way to get really absolute dates on Mars independent of the crater impacting record. And if you have a very small surface, the uncertainties go way up in your estimate of that. The somewhat longer answer is that this is one of the things that we really want to do with the mission, is because that alluvial fan and the time equivalent deposit that's downhill of it, where you can let your imagination guess what might be there, we want to know whether or not that package will then run under Mount Sharp and actually be the older thing that we have discovered or investigated. And the other hypothesis is that it is the younger deposit, and we expect it to abut and onlap the mound, go like this against the mound. And we'll see a geometric relationship. We really won't get into that question until we've driven to what we call this mound skirting units, the very base of the mound. And that's going to be a big part of this mapping exercise that we're doing right now, is to try to find the key places where we could go to see whether it does this or whether it does that. And so we might be waiting a year to get to that part of the mission. However, if you take it in sort of the way that it presents itself right now, most simply, you could guess that it would be younger. And in that case, what's cool about Mount Sharp is that it takes us from the time in Mars's history right down at the base of Mount Sharp where we have clays to the time when we have sulfates, and then maybe 700-800 meters above it, we cross a boundary, and everything up there, its morphologic character, the physical stratigraphy, the mineralogy, suggests that it represents the dry period of Mars. And I, for lack of a better contextualizing phrase, I like to refer to this as the Great Desiccation Event of Mars. This is the thing that everybody's been wondering about. How did Mars go from being a wet planet to a dry planet? And we hope to cross that boundary and get at that. But as you know, if you draw an analogy to the way we've studied the Earth, we have things like the Great Oxidation Event. It turns out, and initially we think it's a single unidirectional trend. But then it turns out, as you do more research, you see, well, there's precursor events and there's events that happen after. And I think a lot of people now think that there was a phase in Mars's history in Amazonian time when it may have been wet. And it just wasn't wet for a long period of time, and maybe Gale Crater has just captured one of those younger pulses. And the amazing thing about it is that we may get to investigate this broad range of environments in Mars's history. But TBD on the actual stratigraphic relationship.
Okay, we have another question actually in the row right in front.
Hi, Irene Klotz with Reuters. I have a couple logistics questions and then a science question. Do you, and I know this might be for the next panel, but do you know yet if another trajectory correction maneuver is going to be needed?
It may not, but we should wait for the next panel to answer that.
Okay. And for John, if the checkout and everything goes as planned, when do you expect science operations to begin?
It's sort of, as you're guessing already, I mean, it's kind of a fuzzy progression. We land and we start checking things out, but the important thing to remember is every time we check out a science instrument, we're making a measurement. And so when we turn them on, first thing we do an aliveness test. And then after that, we do a health and safety test. And in the course of doing most of those tests, we actually acquire data that comes back down to Earth that gives us some sense of what's going on. But until, we'll do that for about the first, 12, 14 sols, roughly. The first 2 weeks will be spent putting up the mast, using the instruments that are associated with the mast, doing remote sensing. And then after that, we have a little break in the action we call intermission, where we're going to be able to drive for the first time. So when we do the second part of checkout, when we want to put the arm out, for example, we'd like to put the arm out on something we think is interesting. So we might drive a couple of meters, a few tens of meters, and along the way, we're going to do some more characterization of the cameras. We're going to do some characterization of the ChemCam. We're going to turn SAM on for the first time and do a sniff of the atmosphere. And that's an engineering checkout, but it's a science measurement at the same time. And so then after that, we'll, a few weeks after that, we'll be doing the contact science instruments, and somewhere between a month and 2 months after we've started, I would guess we will have collected the first soil sample and maybe even drilled the first rock, roughly. So it'll be staged in sort of days, weeks, and months until we're really ready to go and we get the keys to the rover.
Thanks. And I guess another kind of big picture science question. You mentioned the SAM instrument. Will the rover have anything that's going to be able to characterize any atmospheric methane? And if so, would there be any way to distinguish whether it's geologic or biologic?
That would be the tunable laser spectrometer, which is part of the SAM package. And it's during the intermission, we're hopeful to be able to make a measurement when we do the instrument checkout. However, again, just to condition expectation, that measurement will not be long enough to give a definitive answer to the yay or nay question about methane in the atmosphere. We need a longer period of time to do that, so that will wait till slightly longer in the mission. And in the event that we detect methane, what we can do is determine the isotope ratio of the carbon that's present in that methane. And even if it turns out that it's very light, which is often what's associated with methane on Earth that's of biogenic origin, there are abiotic sources that also produce methane. So we'll always be in this somewhat equivocal situation of saying, it might be or it might not. But the first thing is to just ask, is there methane in the atmosphere or not? That's what we're trying to do.
Okay, and Irene, your first question gave me a perfect opportunity to remind everybody that we do have, this is the first of 2 news conferences this morning. At 11 a.m. Pacific, 2 p.m. Eastern, we will have our mission overview engineering news conference, and any questions about entry, descent, and landing will be addressed there. But in the meantime, I believe we have more questions here for our science panel. Let's go ahead in the first row.
Yeah, hi, this is John Russell with Reuters. When I told my wife that I was coming up here, the first thing she wants to know was, when are we going to put somebody on Mars? And so the perception is, how big a step is this in that process? And then secondly, how excited are you guys, about what's going on?
Part of the design of the Mars Science Laboratory was, in fact, to create a capability to get a metric ton to the surface of Mars. And hopefully we've done that. And that is going to help us go in a long way of understanding how to get to the surface of Mars safely with large payloads. I think also as background and some necessary steps, we need to make measurements at Mars to understand the planet, not only in terms of the science, but what it can tell us in terms of what would be the safest way to get to Mars and have humans go there and explore. And RAD is a great example of one of the things that we're doing that's going to help the science, but also will greatly inform what we need to do for future human explorers.
To go back to the putting someone on the moon, how big a step is as far as being able to do this job from back then to doing what we're doing now? Because there's a perception when you talk to people about exploration that nothing has changed since then. We've been stalled, but I'm just wondering from you guys how wrong that perception is.
Well, one of the things to keep in mind is actually sending a robot to go and basically make your measurements is a difficult thing to do. We have a hard time doing that here on this planet, much less sending it to Mars. And we have another major issue with sending humans, sending them to the moon compared to sending to Mars. We have a very different radiation environment, and we have a travel time that's a big issue. I mean, Mars Science Laboratory is taking 8.5 months to get to Mars. To the moon is a 3-day trip. And that makes a huge difference in terms of, oh, something went wrong, let's go home, versus, sorry guys. So there's a lot that goes into it, and then you fold in, because of transit time, how much more stuff you have to take with you, you have to get back. So we're not stalled at all, and I think we've made tremendous progress in certainly getting robotic effectors to do our job so we don't have to send humans right away. And we can learn a lot of background information and find out if there are ways we can go to Mars and actually use the resources there to make the whole trip a little more cost effective.
Okay, I think we have a few more questions. Let's get a mic over here to the, yeah, go ahead. John?
John Johnson. Speaking of the habitability issue, on the trip to Mars, what would that big spike have done to a human crew?
Well, so John, the spike inside the rover was observed by RAD would be sort of the environment that an astronaut would experience. And I think the spike in and of itself isn't lethal, not that size of a spike. It would have to be a much larger spike to have short-term risk from that one particular event. But when you consider a long-term mission to Mars, we're talking 2 to 3 years round trip. It's all cumulative. So it's the background galactic radiation environment as well as the numbers of those spikes as they add up over time and the size of them, and then what sort of shielding you can provide on the surface as well.
Well, given that, then, what have you learned about the potential for a human crew to survive on the trip?
Well, so far there's 3 parts. There's the cruise out, there's the one way out, there's the surface time on Mars, and then there's the cruise back. Cruise back we would hope would be similar to the cruise out, although you can't really predict those the solar storms or the solar particle events. But what we've learned is that the contribution to an astronaut's total lifetime dose limit, which NASA has established, it's a non-trivial fraction of it. It's a significant fraction. We're still analyzing those and reducing those data, to get the exact numbers, but it's a significant contribution to an astronaut's career limit for radiation.
Okay, we have time for a couple more questions. Let's go to the second row here. All right, that's fine. Go ahead. We'll get to you, too. We'll just go in the order the mic appears. Yeah. Okay, go ahead.
You want me to go ahead? Okay.
Yes, sorry about that.
Okay. One question each for the 2 mics. Mike Malin, describe the advancement in data storage, image storage that you've got with MSL compared with Spirit and Opportunity.
Okay. These cameras are significantly more advanced than the Spirit and Opportunity cameras, though they are probably not as advanced as something you have in your pocket. The cameras have larger detectors, and the storage, we have the equivalent of an 8 gigabyte card in the camera. So we can store in the camera without having to rely on the rover to store it in its memory. Each camera has an 8 gigabyte memory, and so the total cameras have 32 gigabytes, which is a fairly large amount. I'm not sure if it's the largest amount that's ever flown in a NASA spacecraft, but it's probably pretty close.
All right, I think we had a question. I'm sorry, Craig, did you have a follow-up?
Yeah, I had a follow-up. A broader question for Mike Meyer would be in the context of the 21st century, in terms of laying a true, highly detailed database on Mars. Kind of wax eloquently, if you would, there on just how significant MSL will be, no matter what future missions are selected when.
Yeah, the Mars Science Laboratory was conceived more than 8 years ago, and it was recognized. We actually went through several committees looking at what was needed to be done to have an astrobiology go to Mars. And essentially, for the first couple of tries, the answer back was, we really can't do that. We don't have the resources, that's a little too advanced. And we finally came to MSL and the opportunity to select the instruments. And these are fantastic. This is the first roving analytical laboratory we've sent to any planet. And it is a laboratory. It's amazing that we can do chemistry and we can do mineralogy there on the surface. And in many ways, any geologist would die to have something like this with them when they're out in the field. So It's a tremendous asset. And the degree of engineering that goes into making this rover to last the whole Mars year, and to have these instruments fit inside the rover or on the outside of the rover, and have them integrated, it's a tremendous challenge that I think that NASA and the science team has really stepped up to.
Okay, we have time for a couple more questions, so let's get the mic over to, there you go.
Hi, Nadia Drake with Science News, and I'm wondering if we know how Mount Sharp formed and if there are any analogs on Earth.
It's a great question, and the science team is, the question was if we know how Mount Sharp formed. The short answer is no. We'd like to address that. There's a number of hypotheses. Part of answering how it formed, and I presume by that you mean the shape that it has today? Yeah. Is understanding how the layering formed in it, what materials the mound is made out of, and what they represent in terms of the mechanisms. I think that this is a feature that was recognized by Mike Malin and Ken Edgett going way back to probably the early days of mock observations, and they made an incredibly important observation, and that is that Gale is not alone. There's a family of craters that they sort of drew an evolutionary tree, and pointing out that these big Noachian craters that are 100, 150 kilometers in diameter are filled up. And then you can go and go a couple hundred kilometers away and see one that's partially eroded back, and it begins to get a little bit of a moat. And then you go in another direction, a couple hundred kilometers, and you see one that's more eroded back. And Gale seems to be the one that's at the evolutionary end of the spectrum that's the most eroded back. It's too high to be the central peak associated with the impact itself. We can see the layering from orbit that tells us that the material is not massive, it's not impact ejecta. It's hard to get around the case that it was once filled up, that crater was once filled up. These are always difficult stories to come to grips with scientifically. It becomes a story of ships that pass in the night. Everything's been eroded. Nobody was there to see it. How do you go about testing this hypothesis? And it's not going to be easy, but we're going to try.
Okay, I think we had a question in the row right in front. No, the orange, red, coral. Maybe not. Does anybody have any additional questions? Okay, let's hop across the aisle to... Yeah, this is going to be the last question, right there. Raise your hand higher, please.
Are you talking to me?
Okay.
Yeah, hi.
Go
Conan
first.
Nolan, NBC Los Angeles. Dr. Meyer, you touched on this a moment ago, just very briefly, though. The public does remember Spirit and Opportunity. We remember Pathfinder. It's a much larger rover this time. The sense is that incrementally there's been advancement of our understanding of this planet. Is it your opinion that this could be more than just that the kind of instrumentation you have here, not just the imagery, is such that could lead to discoveries that far outweigh anything we've seen before on any of the rover missions prior to this one?
Well, there are two aspects. One is by having this instrumentation, we can confirm mineralogy that we think we see from space. And so that can be huge in terms of just globally looking at Mars and going, oh, it's a different mineral than we thought. This means that the history is slightly different. The other thing, and part of the reason why I like to view this as the first astrobiology mission since Viking, is that we are going to measure organics on this roving laboratory. And one of the big pieces that we're missing for understanding habitability is we have the water, we think we have the water, we're going to confirm it with Curiosity. I think we have the energy sources, and we have to find some discontinuities, that sort of thing, but I think we're relatively confident that there are energy resources on Mars. But what's missing is we haven't seen the organics. And so one of the big measurements that Curiosity is going to make is finding, hopefully, or not, finding organics. This is a big question. We have good theory that suggests that there should be very refractory organics still there on Mars available in many of the, not many, but some of the places that we look. But we don't know. We don't know the problem. We have this radiation environment on Mars that can destroy organics. So even if it was there, it may be hard to find a place where it's been preserved. But I think that measurement is going to be one of the key ones that will encourage us or discourage us in terms of what Mars was like early in its history or even today.
Can I add to that?
Yeah, please.
Let me just add to that a little bit. I think one of the things that will really distinguish this mission is, in addition to the larger size rover and the payload, which in one sense may seem incremental, the fact that it's really the science problem that we're addressing that is presented by the field area. This Mount Sharp that sticks up gives us this time dimension that has never been explored before. We did it a little bit with MER. All of us that worked on the Opportunity rover got really excited with a few meters of stratigraphy, a little tiny snapshot amongst billions of years of the history of Mars. When we went to home plate with the Spirit rover, we got another few meters. This time around, we have hundreds and thousands of meters. Every significant problem that has to do with the early evolution of the Earth, the interaction between life and environments that causes the tempo of evolution, that is exactly the way that we approach these problems, by taking hundreds and thousands of meters of stratigraphy as sort of a tape recorder of the way that the planet changes to understand what happened. That's what's really new about this mission.
Okay. Thank you. And we are unfortunately out of time for questions. If any reporters here still have questions, please check in with the newsroom and we'll try to help you set up an interview or an opportunity to get your question answered. Okay, just a reminder that in less than 10 minutes we will be starting our mission overview engineering news briefing, 11 a.m. Pacific time, 2 p.m. Eastern time. And in the meantime, please stay tuned. We will be replaying all the visuals that you saw in the Science News Conference. And again, a reminder that lots of information is online on the mission, the Curiosity rover, online at www.nasa.gov/Mars. Thanks for joining us.